and then I will discuss about some low energy behavior of the gravity theory, and then I will move on somehow the boundary theory in two-dimensional slasher conformal field theory, and then the next step I will discuss about the slasher amplitude and OPEs. Somehow this is very important subject in the context of the collinear limit in the scattering amplitude. And after that, I will discuss about some of the soft symmetry. Basically, in this case, also another very important concept for the soft limit appears in the context of the Weinberg soft theorem. And then
it's not switching slides.
yeah, and then if I have time, then I will talk about my list of works. Okay, so this is introduction. So I was impressed by the Streaminger paper appeared last May. In here, the title was W1 plus infinity and the celestial sphere. So maybe I will somehow describe this what W1 plus infinity at the end of my talk. And this is somehow the two-dimensional sphere, but basically in here we call this is the heavenly sphere was a celestial sphere. Basically, this is the two sphere. So in this paper, he somehow connected somehow the some infinite symmetry in this paper. So maybe this is my personal motivation where I'm working on in this direction. Then what is slasher holography? So basically in the four-dimensional we can consider asymptotically flat space-times in here, four-dimensional theory, and then we have two-dimensional boundary theory. So this slasher CFT somehow has some similar structures in compared to conventional CFT, but there are some differences in here. So I'm not sure whether this citation is correct, but somehow maybe there are many other papers on this particular subject. So people were trying to understand what are this holography. I mean, you know that we are familiar with the idea of CFT correspondence. So somehow the long-term goal of this holography, somehow we want to understand what is a non-part of the definition of the quantum gravity, and how do we discover some symmetries, the hidden symmetries, and how they appear, how the generators of those symmetry arises in this context. And here's my references. So basically, the first one is maybe some other lecture notes by Streaminger. And the second one appeared as a Snowmass paper, so it appeared last year. And also we have two lecture notes by Pestowski, Liu, and also whom I enjoyed very much her lecture notes. Basically, also she gave a talk, Galileo Galilei Institute, this year, and maybe you can see her lectures in here, and also Juice PhD thesis paper, and also we can have many talks during the conference and the workshop and schools and lectures. Okay, so now I will continue to move on the infrared structure of the gravity. So I drew in here in the blackboard. This is somehow the well-known the Penrose diagram. So we want to understand how we can get from the no boundary, but we need to have some specific boundary. So we can start with this Minkowski metric, so -1, 1, 1, 1, and we can change the variables by using this usually standard spherical polar coordinate. So as we can see that t goes to -infinity, infinity, and I goes to 0 to infinity. So we need to somehow go the another change of variables. So we know that from the classical electrodynamics by Jackson's, we know that somehow the retarded time and also advanced time, we can take the c equal 1 unit, then we can introduce this u and v coordinate. And then metric can be written in terms of this in this way. So we have here's two-sphere metric. And furthermore, if we look at the undergraduate general relativity textbook, we can also see that this kind of change of variables, capital U, capital V, then we know that the tangent function is somehow ranges from the argument u and v somehow is -π/2 and π/2 in here, and we can rewrite this metric in terms of in this way. So you can easily see that those using some trigonometric some properties in here. Then still the good thing is in here we have some compact range for the new variable u and v in here, and we can check somehow the old variable from the new variable. We can have this kind of simple relations, but still we have this overall factor somehow we have some diverse due to this factor. So we can introduce the conformal map by observing those overall factors. Then we can have some good property of the metric in here. And furthermore, we can introduce capital T and capital R given by this linear combination, big U and big V. Then we arrive this metric, and in here we have, you can see that this dr square sine square r, and we have the two spheres. So basically this is somehow a metric for the three spheres. So we have this one-dimensional r times three spheres. So we can visualize in the cylindrical shape. And then inside of those shaded area inside of the cylinder, we can just simply unknow those regions. Then we will end up with this kind of Penrose diagram. But we can also this somehow sometimes we can use the full diagram, but sometimes we use only the part of this one. So you can see that here. So we have the future null infinity and this test null infinity, and we have also in the usual notation we had I plus I0 I minus is somehow this future timeline, this past timeline, and spatial infinity appears in here. Okay, then we have the two boundaries in here. Okay, then, yeah, so this is what I explained before in here. So now we are interested in the massless particle rather than massive particle. So massless particle can go on from starting from here to we have the 45 degrees, and then once arrive in the r equal 0 region, then it starts with in this direction. So we have this kind of features in here. However, the massive particle somehow is moving, starting from this timeline, past timeline, or past time like infinity, and then go somewhere in here, and then go in this direction. Okay, so I drew in here. This is RT blackboard diagram, three-dimensional diagram. So we can just specify those positions RT in here, 3 places, and also, yeah. So that's what I meant in here. So we have massive particle case. We are moving from here to in here. And sometimes we introduce Z and Z bar notation. So in this case, we can understand somehow the particular theta and particular theta case. We have north pole and south pole. So we are interested in some scattering problem in Minkow's space. And then one can, I checked this explicit relation. So for given rectangular coordinate, x1, x2, x3, and also we have retarded time, and in terms of those z and z bar, and also r, then the previous minus dx0 square plus dx1 square, dx2 square, dx3 square can be written in terms of in this way. So you can see that I will just explain those metrics up here very soon. So now we add the gravity in this Minkow's metric. So we assume that they are moving, for example, gravitational wave somehow moving outward, and spherical symmetric wave. And then Bondisas coordinates, somehow we take some zero value further metric components. This is retarded time and radial coordinate r, and also we have two angular variables in terms of z bar. So then metric can be written in this way, and then we can associate with this retarded Bondi coordinate and the previous Minkow's coordinate, and then we impose this polar condition on the metric component. Under the we can take the same value of their retarded time and the angle variable z bar, but we take the r goes to infinity limit. Then according to this BMS work in 1962, the metric can be written in terms of in this way. So we have the first line is about the known Minkow's metric, but still we have some I dependence appears in here, 1 over r, but the other quantity somehow depends on the other u and z bar dependence. Okay, so this is somehow the previous rectangular coordinate in terms of the r, z bar, and also we have retard time. So the metric is given by this one. But yeah. Okay, then there appears 3 quantities. MD is somehow the Bondi mass, so-called Bondi mass by energy aspect. And also we have the capital N is angular momentum, and we have the capital C is given by through this relation. This is so-called Bondi-induced tensor. Therefore, that appears in the previous metric. And then we introduce some other what's the definition of the asymptotic flatness condition. So in Minkov space-time, we have the this kind of V derivative acting on this Minkov flat metric will give us zero. So we simply take R goes infinity limit under this same condition. So that's somehow our asymptotic flatness condition. And then the previous under the coordinate, so we have basically we can combine these two lines in here, so only the containing the f in here, and here's the yz is somehow some vector field on the two spheres. What BMS found was this is super translation is somehow not. This is super means nothing to do with supersymmetry because it appeared as 62, but usually supersymmetry, the terminology of supersymmetry appeared I think the 70s. So then somehow what they found was that they generalized the previous translation to the super translation. So in other words, those f somehow depends on the arbitrary function of the two spheres z plot. So this super translation somehow the direction dependent time translation, and yeah, under the boundary, and also includes the ordinary space-time translations. So the one point in here somehow the asymptotic symmetry group of general relativity is doesn't reduce to the one for the special relativity in this case. So now the Poincare group is somehow the semi-direct product of the Lorentzian translation that can be generalized by this BMS group. So we take the translation, is changed to the super translation. We have the infinite number of the symmetry. But people they say that the BMS, but I have no idea why the second author this author is missing. But yeah, BMS stands for I think Bondi and Metzner and Sass. But if you know any reasons, please.
Yeah, it's because it's a communication to the Royal Society. In communication of the Royal Society, you can have a single paper, but with different independent parts in it. So van der Burg gave an example of gravitational waves, and it appeared as a separate paper with a separate author.
I see. So the BMS is correct.
I mean, BMS, I think it's defendable at least. I mean, calling it BMS is defendable.
Okay, so in particular case, f and y, z, we have the usual four-dimensional, global transformation, and also we have the Lorentz case in here. And furthermore, if we just look at the first part of the previous killing vectors, then somehow it contains only the yz, and I think around after 50 years later, there are several papers in here, but somehow they somehow found the super rotation. So in this case, we can somehow the BMS is given by this Lorentz times super translation, but somehow Lorentz part it can be generalized by associating this super rotation. So in other words, the yz is somehow the meromorphic function where we can allow some finite number of poles on the two spheres. Okay, then this local conformal symmetry can be realized as a Virasoro. So we have the extended BMS is given by left hand the Virazor right hand, Virazor, and we have the super translation. And also the Stranger pointed out this YZ, somehow the candidate for the meromorphic function, somehow can be taken in this the famous safety paper.
How did Virasoro appear? We're talking about super rotations and super translations, right? How did Virasoro you mentioned that DMS is super rotations and super translations.
Yeah, but those super rotation can be generalized. We assume that yeah, here's the YZ is somehow can be any function of z case power. So that means we can from the global transformation to local case, then we can get this Virazor case in here.
So one Virasoro is for Z and the other one is for Z bar.
Yeah, that's G bar, yeah. And furthermore, in this paper, they further generalized by looking at the diffeomorphism of two-sphere in here. But let me just add one comment in here that last August, the Schwartz wrote some paper by with this title, and basically he somehow introduced the generalized Virazor generator. I mean, having non-zero H and non-zero H bar, and then he just computed some algebra, but the Jacobi identity doesn't satisfy, so he introduced the spin operator having the H bar is equal to 1,1, and he just wrote down the full commutator relation, or OPEs. It's a rather complicated expression, but it turns out that according to his analysis, somehow those two-dimensional diffeomorphism symmetry implies conservation of the conformal spin, but according to under the within the slasher holography, this implies that four-dimensional sense we have some helicity of the particle. They should preserve, but we know that this is not what we want. So the final his conclusion was somehow those generation to the diffeomorphism we shouldn't consider in this context, but maybe his diffeomorphism algebra will apply to other models, not inside of the slasher holography. Okay, so that's one comment, and also if you just look at the Streminger's lecture notes, we have some triangle, so memory effect, asymptotic symmetry, and the softest or the theorem. They appear as an IR region, but four-dimensional theory, and people hope that maybe the experimental evidence will appear, I mean, soon under this memory effect. But I will discuss about those things. But basically, I will focus on only the relation between asymptotic symmetry and the soft theorem. Okay. And then, yeah, and also we have for the photon we have the soft theorem, and graviton we have the reading and sub-reading and sub-reading soft theorem. So we will see some relevance in the later part. Okay, so yeah, so we have between the relation between the asymptotic symmetry and the soft theorem, we have the known the word identity. So through the word identity, we can make the correspondence between these two sides. Okay, then from the lesson of the Adis-Swift correspondence, we can think about what are the boundary theories and how the symmetries, both sides are they are matching, and what are the symmetries and what are the spectrum. So this is second part, and third part, I just moved from the four-dimensional bulk theory to the two-dimensional theory, so-called the celestial conformal field theory. So we know that the isometry group of the Minkowski is given by this Poincare, again the semi-direct product of Lorentzian translation. Here I just introduced some subgroup of Lorentz group, so plus 1,3 is given by SL2C divided by Z2. So if we include the parity and time reversal, then we will obtain the full Lorentz group, O1,3. Here the Z2 is somehow we know that ABCD are the element of the SL2C, the complex numbers. So if you change the signs, then we will have those Z action in this expression. Okay, so now this is the usual contents in the conventional SET textbook. So we have some global conformal transformation given by L plus minus L0 L0 bar, and so they are somehow the non-singular Z equals 0. We have some translation, rescaling, and also if we are using the complex Z is given by I exponential I theta, then we have L0 L0 bar is given by this expression, so-called dilation, and we have the rotation, so this angle phi. And we have the special conformal transformation, and then we will end up with those SL2C divided by Z2 is somehow the group of conformal transformation on the Riemann sphere. So we have complex plane plus Z equal infinity point. Okay, so this is the usual SL2C element, and we have some constraint in here, and the transformation is given by this this. Okay, then we need to understand what is Lorentz transformation in terms of the previous ABCD in Bondi coordinate, and then we will have some large R limit, and we will have the appropriate transformation for the R and U with some angle dependent rescaling. Okay? So we want to understand, we want to somehow read out the S matrix, 8 S matrix in terms of the SL2C covariant way. And here's the boost eigenstate. So what this means, so we can take some 4 momenta Q mu is given by time component and X3 components that corresponds to the nose pole, and then according to the next slide we will see that the explicit solution for this one is given by this particular combination. Then we can check that L0 L0 bar in terms of those boosts through the 3 direction. So we can simply add this kind of differential equation onto this solution. Then we will end up with those is given by delta times phi. So this is somehow the boost eigenvalue equation. Furthermore, we can take the different sign, then we will have 0 and also L1, L1 bar, X1 phi will give us some known the highest weight with respect to so 1,3. So that's somehow the boost eigenstate in this particular example. Then this dilation in previous two-dimensional language that can associate with the boost in here. We have this some small L0 plus small L0 bar is given by this correspondence, and the rotation also 2D rotation can associate with 4D rotation in the fixed direction. Okay, so from the recall that the previous x mu spatial part is given by the proportional to this kind of things, but we assume we require that this is somehow the null, so q square should be equal to 0, so we can easily compute whether they really vanishing or not. So we can have this kind of parameterization, and then according to previous z prime bar, we can check this SL2C Lorentz transformation, and massless spin can be characterized by this plus minus omega times q mu. So plus minus depending on the outgoing and incoming particle state in here, and yeah, so those direction is given by can be encoded by this q. Therefore, we according to the this holography dictionary, omega in 4-dimensional can be associated this conformal weight delta, and 4-dimensional helicity somehow is associated with 2-dimensional conformal spin. Yeah, based on this paper. Okay, then in order to from the momentum basis in the usual scattering amplitude, we can go the boost basis by multiplying those integral pieces. So this is nothing but Fourier transform. So we can apply those Mellin transform in each of the n external particle energies. So schematically, we can write down this matrix from this standard momentum basis to the boost basis. And here, for example, this plane wave can be associated with using this Mellin transform. And you can see that the final expression depends on capital X, and that dependence appears there through the period Q mu.
So the states are a superposition of states of a lot of energy.
Yeah.
It's not that you have one energy, it's going to be an infinite combination of the tower of the other states.
Yeah, so yeah, basically I will comment on it later, but we can take the omega goes to 0 to infinity. So.
Yeah, it's just different bases. Usual momentum bases.
Okay, then according to this x prime, z bar prime, we can have this kind of transformation. And yeah, as you mentioned here, we can just consider that the finite product of those 0 to infinity, the omega divided by omega and omega to this delta power. So 4-dimensional conformal primary wave function depends on capital X at some point in two sphere. So we need to rewrite in terms of the this 2-dimensional conformal primary field, and here somehow the transformation for the general spin. So we can see that here's S dependence in here. Sometimes people classify the radiative conformal primary wave functions under this condition and other general cases. And here somehow I'm not familiar with this kind of product, but their motivation was somehow if we go to the momentum space description, we can somehow construct some creation annihilation operator, but in selecting those creation annihilation operator, we can use somehow Klein-Gordon inner product for the scalar case. And so they somehow mimic those description in here. So we have some bulk operator in here, Maxwell's theory or the pure Einstein theory. So we can think of this bulk operator somehow depends on creation and annihilation operator by mode expansion. And this is the previous one, but in this expression we have those integral forms over the energy. So then we can introduce this slasher operator. So having those delta J and depend on Z and zeta.
Sorry, but are these delta eigenstates, what is do they have finite energy? So if you compute just the expectation value of energy on a state with a fixed delta, what do you get? It's the infinity, 0, or a finite value. It seems infinite, but I mean, if delta is less than 1, you have a divergence of small omega. Delta is larger than 1, you have a divergence of larger than 1.
In general, delta is some complex number, so real part plus I times some imaginary piece.
Yeah, but I mean, in any case, right, since you have a power, an integral of d omega over a pure power, it can never be finite.
Later on, we somehow introduce omega is somehow much less than some omega star, some cutoff, and then this infinite the range can be changed to 0 to omega star, but then we can use some delta function behavior. Then those integrals can be finite.
But I mean, if they are finite, they are all weighted by the cutoff. All go up to the highest k. I mean, suppose that even delta is 1 plus I lambda, or lambda 3, right? Then the expectation value would be an integral in d omega, I suppose, of an integral in d omega. Then that would be weighted by the cutoff. Everything. I mean, not that there may be anything wrong with that, but it's interesting that these states don't have finite energy.
Are your states normalizable?
Yeah, delta function normal.
Just like
Because of continuous spectrum.
Okay, so let me continue to the next part. So slasher amplitude and slasher OP. So we are interested in this scattering amplitude, and we introduce some AN as a matrix. And as I mentioned before, so we have the Mellin transform by inserting this kind of vectors in here for each omega I. Then the claim is somehow those slasher amplitude can be written in terms of this two-dimensional this correlators in here. So so slasher amplitude somehow transform as conformal correlators, and in the context of the scattering amplitude, we have some collinear limit. So then how do we interpret, how do we describe this in two-dimensional language? So we have particularly collinear divergences, four-dimensional momentum space can be described by if we go to the two-dimensional slasher CFT, then we have somehow the singularity. So that can be understood that from the propagator. So we can take the pi and pj, and process square is somehow we have the pi squared equal to 0, pj squared equal to 0. Then we have the pi the pj. But using the previous Z parameterization, we will have this kind of combination. But if we treat those Z as independent variables, then we will see that for fixed Z we will have this kind of simple pole, so 1 over Zij. So Zij is somehow the difference between the Zi minus Zj. So we have the simple poles in here. So schematically, so we have the one celestial operator and another celestial operator, and right hand side we have the another celestial operator. So then how do we find out those right hand side explicitly?
Quick question.
Yeah.
What goes wrong if you don't? What's the singularity structure like in 3-1 symmetry? It's not a simple pole, I guess.
What do you mean by ends?
You said that you had to go to 2-2
Uh-huh.
to get a simple, to argue that this OPE limit gives you a simple pole.
Yeah.
I was just curious what goes wrong in signature 3-1 or something? Was it?
You mean the 2,2, 1,3, right?
Yeah.
So in that case, maybe we should be careful about those limiting procedure, because in that case, Z bar is not independent one, so they are dependent each other for the 1,3. Then we cannot say simply fix the Zi bar, J bar. We cannot take this kind of divergence structure. So in 1,3 we have a different limiting procedure in here, but here we just fix the Z bar, and then we can take Zi goes to Z0, J.
You would have such a problem with usual two-dimensional conformal theory.
Yeah.
Right? We can always take two operators in complex signature and bring them together and expand the terms of conformal operators.
Just because of unitary, you have a Hilbert space.
But
OPEs
here we
conversion.
don't have-
Central singularity? Depends on the way that you approach.
They're just this it's probably not clear that they're a convergent OPE. If you have a convergent OPE, then you can continue your Z's. You have like absolutely convergent series, right? You can modify each term by phase. That's not gonna like the convergence. It's gonna give you the analytic. But that's not guaranteed here because you don't have underlying relation.
Maybe already that is, but how's delta related? What is that? You said delta is some complex number, right?
Yeah.
That's what is it from the point of view of this category?
Yeah, still it's not clear. I mean, why the delta appears on complex numbers, but still it's But later we will focus on somehow the real and somehow integer value, positive and negative.
What's the boost rate on regular energy?
Okay. Yeah. So it's related to the momentum.
Well, you've replaced momentum with a different like quantum number, right? So no longer momentum is no longer diagonalize translations, you diagonalize boosts. And so energy is not a well-defined notion in these states, but boost rate is. It's the eigenvalue under boosts.
So delta is energy in the Ringler space.
Rendered space.
But Z, when you write P here, you still mean the momentum, right? Or when you were writing Zij, like related to Pi or Pj, those P's are still momentum, right?
No, the direction.
Yeah, those
It's
are-
the direction, it's not the momentum.
Okay.
Okay, so in the collinear limit we have this kind of relation, so we can simply use this parameterization. Then capital P appears in the right hand side, and here somehow this combination, and the energy in omega I plus omega j is given by omega P. And as I mentioned before, so we have the fixed Z bar. We can take the holomorphic limit in here. So then this will somehow arise as the singularity of the OPE. So we use this change of variables, then from the result of the scattering amplitude, this splitting factor is given by this one for the graviton. And yeah, there appears some the virtual graviton splitting to two gravitons, for example, the graviton case. And also we can consider the gluon case in here. And then it turns out that those alpha parameter somehow can be included in this Euler beta function, even though I didn't check the all the details. But if you just look at this paper, then there is some series of change of variables. Then you will end up with those Euler beta function piece and the other part. And we can read off those conformal dimension is given by, in this case, we have delta equal delta j. And here, for the graviton case, we have plus 2 helicity plus 2 helicity, and also the plus 2 helicity. But the important thing is structure constant on the right hand side. Somehow we have the Euler beta function, and we have delta I minus 1 delta j.
So it's a 2,2 simulation.
Yeah.
What is kappa?
Kappa is the somehow proportional square root of gravitational constant, Newton gravitation. For the gluon case, we have the splitting factor is in here, and also we can write down the OPE between the graviton and gluon. And for the gluon case, we have the similar structure in here, Euler beta function plus 1 plus 1 plus 1 helicity. We have the delta I delta j, and here let me emphasize one thing in here, and next part I will explain somehow the soft limit. So according to this relation, you can see that Euler beta function has this kind of, the x goes k, y goes l, but x plus y goes somehow this one. These blue factors can be multiplied both sides. Then we will see that x minus k combine this first object, and y minus l can combine this second one, and also this x plus y minus k minus l can combine the right hand side with the operator c. Then we can just observe those singular piece, and then we will end up with this is equal to usual binomial coefficient. So that's what Changhyun and his collaborator they found during last years.
Can I ask a trivial question? So when you write this equality, the second term is holomorphic in Zi. So where does that follow from the left hand side?
Gij is Gi minus Z.
I know it's holomorphic in Zi, so
Yeah.
why does it follow?
That's the previous divergence simple pole term.
The simple whole term is holomorphic,
Yeah.
regardless of what the delta I and delta j is.
Yeah, that's true. Yeah. So one over Z I J that's
So in other words, if you take like a partial bar with respect to Zi bar on the left hand side, that OP is non-singular.
Yeah, that's true. So for example, if you just partial differentiation with the Zi, then that will
bar.
And also this OC only depends on also the Z bar dependence, and also that we have the regular term. Okay, then what are the soft symmetries?
Sorry, so the reason I ask, because if that's the case in usual CFT, that looks like conservation word density for a current, but here it's not a current because delta I is not necessarily equal to 1.
But we will see that that soft symmetry maybe play a role of those what you are saying. The delta can be
they are like currents, but the dimension is not 1.
Not one.
But there is one with 1.
Sorry?
There is one.
I know, but so there's a generalization of
Yeah,
that.
it's a generalization.
When the spin is 1, dimension not equal to 1, but it still looks like a current.
Yeah.
Okay, so what is soft theorem? So somehow the linear linear relation between some scattering amplitude. You can take the one particle goes to the energy goes to 0 and 65, and also Gatchas Stranger, they studied subleading effect. So now we are considering some tree-level scattering and particles. So we have the momentum P1, P2, Pn, helicity here, and then we consider extra, for example, graviton case. We have this kind of extra particles. So you can see that this is some schematic expression for the theorem. So in the left hand side we have the n plus 1 particle, right hand side is the n. So somehow the amplitude. So we have the low energy means we have those insertion of the extra graviton in. So omega is those energy. Omega is taking to 0 limit in here, and the other amplitude is somehow the same amplitude but without those extra graviton in here. But in here is 1 over omega 1 is simple 4. Omega 0 term, so no omega dependence, and in omega in linear, so we have the various soft factors. They are depending on the momentum and basically differential operators. Okay, so Weinberg soft theorem, according to those duality between asymptotic symmetry and the soft theorem, we can understand that the word identities those. One, for the sub-leading case, we have also soft factors in here, and but in this case, we can see that why we need to introduce the boost identity rather than moment identity, because those if we just look at those word identity, then somehow that is somehow some operator that cannot be diagonalized properly. So we should introduce in here somehow another basis, so-called boost basis in here. Okay, for the photon, we have the reading soft photon, 1 over omega 1 term, and BMS super translation, we have reading soft, so 1 over omega term, and the next sub reading is the omega 0 term, and so on. And also we can understand the Lorentz generators within the two-dimensional context. So we just follow the Viragora generator notation, but somehow this is somehow Lorentz generators, L0, L minus, L1, and here. And if we consider the previous slasher operator in here, then it acts in this way. Also related to the global conformal word identity. And furthermore, this is somehow done by this group. We have some PKL. So according to this one, somehow we can understand this is somehow the weight shifting operator. So if you just remember, delta is sum of those one, then those. If you just add this one, then the previous h plus h bar is equal to h plus h bar plus 1. So this is why we call these shifting operators. But this comes from the previous Q or P, the momentum operator in the previous parameterization. So you can just simply look at right hand side, the omega appears in that expression. So omega, according to Mellin transform, omega power, we have the omega to the delta power. So that's why if you add omega factor, then they will bring the exponent is given by delta with delta plus 1. So that one. But so far we have the mode somehow can be restricted to 0 plus minus 1, and in this case KL is plus minus 1 up, but somehow that can be generalized by allowing the more general cases integer number and happy integer number in here. That somehow corresponds to the BMS super translations.
So you see that the L obey the is equal to 0, Virasoro algebra, the Vic algebra. Right?
Yeah, that's right. So we,
So
yeah,
that's
central is,
but what about the other ones? I mean, the LN. So what is the? I missed. What is the central charge of this of the complete Virasoro algebra?
I mean, but we don't have any central term, so I didn't put the indices, but
So that's for all the L's.
yeah, we don't have any central term in here. We don't have any central term.
It's then I mean there is only the trivial unitary representation and then only another one, right? That is unbounded below. So, but do we expect the representations of that to be unitary?
So only one with a Fermat model. The other one would be some kind of.
No, I mean, with that, when it's equal to 0, it
The
is 0
continuous
Fermat
one
module,
is
because,
zero.
but then there is one, which is simply you take functions f on this circle with weight 1/2 plus an imaginary part.
So it would be the conformal extension of the continuous series.
Yeah, so but there is only, again, and it's unbounded below, so I don't know if that has any importance. So basically the only representation is functions of, I mean, tensors of weight 1/2
This would
plus
be
I.
unitary?
Huh?
This would be unitary.
Unitary, because it's fg star integrated in d theta, that's a unitary
Because
scalar.
the theorems that tell you that only you have identities for Fermat module.
For Fermat module, but this one is unbounded below. You understand? But do we know if the representation of the cell is unitary, or we are non-committal about that in this case?
We don't know, and naive calculations say that the central charge is 0, but I think we also still don't know for sure.
Okay, so now the
I'm sorry, related to that, when you say that you have BMS, in that case you could also have additional central elements, also are 0 in this case. For example, the mixing between the supertranslation and superrotation or something like that. The width part you already said that is 0.
yeah, there's 0, and
But in the case you have BMS.
yeah, BMS case we don't have any central term. Okay, so this is somehow when we consider supersymmetric theory, then we will have a Gravitino and Gluino case. But yes, so here I didn't write down the celestial currents, but somehow we have some corresponding currents according to this case. So yeah, so for the photon case, we just simply insertion of the photon gives us 1/omega 4 in the momentum space amplitude and so on. Okay, so now we construct the celestial operator by taking this integral piece acting on the operator, and then we expand those for, I mean, omega equals 0 region. We can just expand that thing. Then what soft limit means, we can take this kind of special limit procedure, and then we can easily check that by using this delta function structure. So it turns out that it will pick up only OJN. So among the many possibilities, we can only take omega JN. So that means, as I explained previous section, we can just simply take this kind of delta plus n. So delta was minus n. So multiply those things, then we will see that those singular structures from the Euler beta function, they are gone. Okay, so we have here, and I think a few weeks ago, Gilbert also mentioned about the Euler completion, but I just quote this Pestovsky Berlin this year paper, and I'm not sure what agnostic in collision, but they say that some strong statement of this celestial holography that are agnostic about the UV completion. So in the previous integral expression, we just simply consider omega is very, very less than omega. One thing. Okay, then this is the previous expression for the graviton OPEs, and we just this is somehow another derivation to extract the structure constants by using the asymptotic symmetries. And here, yeah, this somehow they here the property of the soft graviton theorem can be used in here, and also we can use this translation acting on the operator and subreading soft graviton condition doesn't have any new conditions, and subreading soft graviton can determine finally the coefficients. This is another way to extract those Euler beta function. Okay, then we can go on by introducing this H. We have the epsilon and this one. So this is done by Guevara, Himmich, Tate, and Streninger. I mean, last year, the March paper, and turns out that it can be summarized by in this way. So you can see that structure constant is given by simple binomial extension, and so we have some descendant in. This is graviton case.
So is H related to the stress tensor of the theory? Of this still the
H0 is
so what happens if you
like related to the stress tensor.
just compute the 2-point function? Do you get 0 because you said the stress central charge is 0, or
Yeah, the like
The one
from
over
the
Z squared
amplitudes
term.
calculation.
1 over z squared term,
Four.
which is
Not only the 1 over Z to 4, it's not there.
oh, I see.
It only starts at 1 over Z.
Oh, I see.
Okay, then we can expand according to this jet and Jeppa usual the decomposition, and then we can focus on the particular modes and where those modes doesn't depend on the jet or jet bar. And then Streninger introduced this particular combination, and it will turn out the very complicated three commutator relation can take simple form. And yeah, here's a P somehow related to previous K notation here, and we have a spot translation, spot rotation, and graviton.
Sorry, just to be sure. So we're currently in a 2-2 signature, right?
Yeah,
I mean, most of the talk is in 2-2, right?
yeah.
And the fact that the central extension is trivial, that also depends on whether you're in 2-2, 1,3.
Not really, right? Like a lot of the amplitudes calculations are really in 2-2 signature. And it follows from the amplitudes calculations, the central charge is 0.
I remember at some point Andy was saying that could be related to the Newton's constant.
To Newton's constant?
Yeah, that's not the case anymore. Where that's still a possibility that's floating.
It could be, but that mode, that current is not actually really the stress tensor. So there's a bunch of currents in this game.
There's some current whose central extension has this
related to Newton's constant. And that one, but that one is not really the stress tensor. So
That doesn't come from the graviton scattering amplitude, it comes from some other scattering amplitude in the first place.
it comes from scattering a mode of the graviton, but there's a particular mode where when you insert it, it has the ward identity of a stress tensor. And that one, naively, when you calculate multiple insertions, you don't see a central term.
So I only just to understand, probably this is too naive, but just to understand that one central term could be related to Newton's constant.
Previously, I thought that the central extension for the Virasoro.
In 3 dimensions makes sense because you start with Virasoro with central charge 1/g, and then you make this ambiguous contraction, and then you find it easy.
Yeah.
4 dimension, I don't know.
Just remember hearing this from it.
Okay, then finally we have the 3 commutators. One of them is given by this one, and yeah, maybe I will. Yeah, this is some other transfer, and we have the translations. Okay, so can I have 3 minutes?
Yeah.
Okay, so let me just explain and describe what is W algebra. So basically it done by, originally the Jamlojikov, now who is in Stony Brook around 85. So as far as I know, this capital W somehow maybe after that alphabetical lettering here, and we have the small w and capital W, and infinity means we have stress energy tensor. We have the conformal spin 2 and 3, 4, and so on. And in this case also, but compared to the small w, we have the big W as nonlinear. So we have in general nonlinear is dry, and on plus infinity also we have 2, 3, 4, and so on. Then additionally we have the spin 1 conformal dimension current in here, and also we have small w1 plus infinity can be also interpreted that way. And this is somehow the review paper, Phillips report, according to this W symmetry in CFT. Okay, so again, this is the Stranger's paper, and I just wrote last year and the beginning of this year.
How is the small W infinity related to the usual capital W infinity?
So if you take the large and goes to infinity limit, then you get from the capital W to small W. That's why
you remove the nonlinear.
Yeah, that's what. Yeah. Okay, so this is the basic material I'm using, and you can see the super BMS. I didn't explain detail, but what they found was they somehow computed scattering amplitude at the collinear limit. So they somehow write down all the non-trivial OPEs, but right hand side you have the bunch of the Euler beta functions, but I can take the previous whereby Kimmich, Pate, and Schreminger's various contour integrals. I took that scheme to this example, and then I get some result. So, for example, we have the colloidal and gravitino in here, so we can also can see this kind of fermionic piece, and also in here, this one also related to paper in here. Then the question is, then for given those commutative relation, how do we interpret two-dimensional W algebra? So that was given in this topological W infinity algebra by Hope et al. And also I include another piece of the coming from the celestial gluing operator, and then and also there is another work by Odake and his collaborators according to this SEN piece. Then so this is the previous Schreminger's and his collaborators' result in here. Graviton, gluino, and gluon, and graviton, gluon. case, and yeah, this is somehow the those paper by the Parkas, 1989. Okay, and then I just add all those extra pieces coming from previous analysis, and that will give us some precise relation between the those two results. This is somehow the open problems, but this is not my original idea. I just took some piece. So we have some celestial sphere, and how do we connect those one in the string world sheet? And also, how do we proceed for the massive case? So I mean, we were talking about the massive case, and also the loop amplitude can be obtained through the string amplitude at one loop, and maybe the last one is here. Maybe we need to understand what is celestial safety in this particular case. Okay, so I will stop here.
So can I make a question, because it's related to the comment of Matthew? I never thought of it, but in these theories, usually there is a symptom that the theory is not unitary, which is the conformal dimensions are complex.
Yes.
Apart from that, we have suspicion that it has a vanishing central charge and all vanishing other possibilities of having central elements, even in PMS also. But then there is this possibility that there is this unitary representation that have complex conformal dimension. I never sort of,
yes.
It's hard to understand why they are unitary, because usually you associate conformal dimension with energy or something. But it doesn't matter. From the
They are
point of view of
similar
algebra,
to the continuous series for
SL2.
for SL2, yeah.
And so it's still a possibility that the theory is unitary, even having this. No?
Well, anyway, depending on what you want.
Because
Do you want
in the light of this, I don't know, at least it's non-trivial, right? If there are these representations, which are not Berman modular representation, but still it has a unitary representation.
It depends on what you mean for a theory to be unitary, right? Is having unitary representation enough, or do you actually want a Hilbert space? I mean, one unitary representation, or a collection of unitary
Well, yeah. From the point of view of having unitary representation, at least the states of your theory, all of them have a positive node, right?
Do you want to have a vacuum?
Not necessarily, right? At least not in this. I mean,
You don't, here certainly don't want to insist on that. That's being narrowed down to the symmetry.
it's not.
What the rule is, the rule of the game.
Sorry?
Yeah, so what is the rule of the game for the celestial here? Like, what are the principles we should insist on? I guess we want to have OPE. We probably don't want to insist on the presence of the Hilbert, existence of the Hilbert space. We want crossing. OPE crossing, and what else?
Yeah, and I think we don't know is the question. Yeah.
At least we want the amplitudes that describes to be unitary.
Yeah, certainly.
Maybe that's like unitary, unlike ADS, right?
Yeah.
Unitarity in the bulk is not the same thing as unitarity.
Yeah, definitely.
Right. So
Yeah.
like when you say you want a unitary representation with respect to what norm is the first question you need to ask. And then why should you why should that be a guiding principle?
I guess eventually we want to ask, for example, how do you translate the usual unitarity of S matrix into some general criterion for the celestial CFP? That's on top of the existence of OPE and crossing.
That's not known.
And that would be an interesting question, because unitarity and causality of the S
Exactly.
matrix
Yes,
can be
yes,
used
exactly.
to
Yeah.
derive the Dyson series.
Yes, yeah.
Now you will study optical theorem. What does optical theorem mean? The elliptic sphere.
But do we have some simple examples that tell us whether, whether the naive unitarity is true or not? Like so, not free theories, because then the S matrix is a bit too trivial, but some very simple theories where we can say, this representation is not unitary.
Sorry, unitary with respect to like the usual conformal theory notion.
Yes, so suppose you have the actions here of a Virasoro of a bit algebra. It's Virasoro with central charge. Right? Then, at least under very mild conditions, and there is a condition that you have a finite number of states at each energy level, there is only one unitary representation, and for that unitary representation, the delta, the weight, is 1/2 plus an imaginary number. So maybe, if you find that the real part of your operators is not 1/2, already you know that the representation is not unitary.
So very early on, right, they ask what conformal weights, right? So you go from momentum space to plane waves, and you ask what set of conformal weights, right, cover the plane wave basis. And this is where I think it's either 1/2 or it's 1 plus an imaginary number. That's the answer for the conformal weights.
I see. Well, yeah, I know that.
It's the principles here.
But it's not, because it's a highest rate representation, so they do this analysis that is described, right? So it's,
In that case, it's the highest way. So
It's
it's a
highest
Berman
rate.
modulo, but still having
it has
the
highest
feature of
rate
being
with complex weights.
This is
Yeah, so
the principal series, right?
Yes, but
It's highest rate
yeah, but it's a principal series, but bounded from below. That if there is Berman modulus.
Yeah.
I see. So, and we don't know what unitarity of the S matrix implies.
People have so every statement you ever have about the S matrix, you could just brute force rewrite it in a new basis. And so somebody, I think Changhyun, they rewrote, I think at a particular, at some order in perturbation theory, they wrote down what unitarity is for the optical theorem. But there wasn't a general lesson about this simple property in the dual fluids to be, that would be what you would want, right? Not just a specific example of what it looks like.
Also, you mentioned that these deltas are just the eigenvalues of the boost operator, or if you want the time in regular coordinates, right? In a regular slicing of flat space. So isn't that enough to say that that you should have a unitary representation of that group, at least of time translation? You should have a Hilbert space, right? And even if you're in regular space, it's not that regular space means that you have unitarity.
You also probably want Hilbert space to be able to describe different geometries in that space. Like in asymptotically flat, you can have different geometries in the work, right?
No, but I don't care about gravity. I want to do QED first. Then there, shouldn't unitarity be more or less obvious? Am I missing something?
It is true. It is true that radial evolution on the celestial sphere or in the plane is regular evolution in the ball.
Maximum, but then you are saying that if that's the case, then the delta just cannot be complex. If delta is the eigenvalue respect to the Rendeler Hamiltonian, and if you want the unit representation of the Rendeler Hamiltonian in your Hilbert space, then the eigenvalues must be real. So something must have gone wrong.
Sorry, delta is not quite the right. Yeah.
Delta is eigenvalue of K3, no?
Yeah, but it's not quite. Sorry, it's not quite Rendeler energy. It's when you do this thing for plane waves, it's like 1 or 1/2 plus an imaginary part, and that imaginary part is strictly speaking the Rendeler energy. So you do some, you realize. Interpreted properly, the real Rendeler energy, not an imaginary or weird Rendeler energy.
Okay. Then it would be consistent with the, the states gonna go by 1/2 plus imaginary number.
Yes.
Yeah, but that's the problem. Yeah, because this is a typical problem. No, conformal dimension is typically the energy is not the case here, and then it says that it's cannot be unitary, but because the imaginary part of it will be the energy in the case, and this is doesn't set. On the pure Rinder, which is well defined, but the energy is well defined.
Yeah.
So maybe you just have another solution of unitarity. So it's not unusual, not going to the
No, we're talking about unitarity of the full theory.
Yeah, full theory.
The four-dimensional theory.
Yeah, but like if you rewrite this condition of unitarity in special amplitudes, it demands something else, but not like unitarity in the usual sense.
Exactly. It's not what. It certainly is not going to be unitary. It's not unitary, two-dimensional. Okay. If there are no more questions, let's thank Changhyun again.